So for number 4, the one that I was stumbling all over at the end of the second um, SI session, for some reason it just wasn't clicking to me, but I'm pretty sure I've got it all figured out now. This might not be the exact method she uses, but I'm fairly confident in the fact that this is going to give us the right answer. I'm never like 100% sure on anything. Sorry about that if that hurt your ears. I dropped something. Okay. Anyways, bear with me through these. I don't edit them. I just literally talk as if I was in front of you guys. So, yeah. Okay. So this is number 4 on the yellow sheet, and it says carbon absorbs energy at a wavelength of 150 nanometers, and that's your lambda right there. The total amount of energy emitted by a carbon sample is 1.98 times 10 to the 5 joules. So that's going to be the energy of a photon, or of the photons, right? Because the energy that's emitted. It says later on in the problem, calculate the number of atoms present in the sample, assuming each atom emits 1 photon. So if every atom is emitting 1 photon and the total energy is that number right there, that's going to be the energy from the photons. Okay, so with that, this is all we're given, and we want to know how many atoms of carbon. So in order to get to that, we're going to have to use these two formulas right here. If you look at her page, the exact thing that this one says is delta E equals HV, or H nu, I'm sorry, not V, oh god, which is equal to, and then it gives a number negative 2.18 times 10 to the negative 18 joules, multiplied by 1 over n final squared minus 1 over n initial squared, I believe. Yes. Okay, so we're not going to worry about this half because we're not worried about the quantum number. We're just worried about this section of it. Now for our delta E, we are going to be using the E of the photon. If I am reading my paper correctly. Yes. No. For delta E, sorry, like I said, this just as if I was talking to you. This is going to be the change in energy. That's what delta stands for. So when we do this, when we do the math, once we combine these, it's going to end up giving us our joules per atom. And that's because this is what's released in joules, and we'll find out per atom. So you notice we don't have a frequency. So to fix that, to fix our frequency, we're going to rearrange this equation right here that I just circled through. Sorry, okay. To solve for nu, so nu equals, we would just divide by lambda, so it'd be c over lambda. Okay, so now we'll be able to plug nu equals the speed of light divided by lambda into here, and that will give us a new equation, and that's going to be E equals hc over lambda. All I did was took this right here and replaced it with this. And like I said, this will end up giving us, so let's put the delta just to make sure everything's clear. This will end up giving us the joules per atom. Now there's not going to be anything that says atom here. We're just going to know that this is for every atom. And we're given the overall energy. So let's just start doing the math, and I'll explain how we turn this and this into the number of atoms. So H, as you guys all know, is Planck's constant. So H equals 6.626 times 10 to the negative 34 joules seconds. And c is the speed of light. So you can use the 3.00 if you really want, but on her paper it says 2.998 times 10 to the 8th meters per second. Okay. And then we know that our wavelength is, let me change colors. Our wavelength is 150 nanometers. So if you convert that, so times 10 to the 9 nanometers for every meter, that's going to give us 1.50 times 10 to the negative 7 meters. This is the number we're going to use because we want meters to cancel. Alright. So our lambda is going to be equal to 1.50 times 10 to the negative 7 meters. So let's go ahead and plug this in. So our energy for every photon is going to be and that's the same thing as this delta E, we're just using the energy of the photon. Yeah, sorry, just double checking something. Okay, so energy photon equals 6.626 times 10 to the negative 34 joules seconds times 2.998 times 10 to the 8th meters per second. That's all going to be over our lambda, which is 1.50 times 10 to the negative 7 meters. Okay, cool. So we've got this part set up. Let's cancel some units and do some math. Seconds cancel, meters cancel, and that's going to leave us joules. So, since each atom emits one photon, this is going to be interchangeable. So that can also be seen as energy per atom, right? Because it's a 1-to-1 ratio. So when you do all this lovely math here, you're going to get, and I believe I rounded my number, but should be in the ballpark, 1.23 times 10 to the negative 18 joules per atom. Right, because like I said, we were figuring it out for each photon, which is the same thing as figuring it out for each atom. Perfect. Now, how does this play into everything else that we're doing? That's like pretty ugly to look at. Let's kind of get rid of this. So this is our overall energy. So maybe just to make this less confusing, we'll just call this our overall energy instead of E photon. So energy is equal to that. That's overall, and we now have our energy per photon, or per atom. I'm sorry, which is the same thing as energy per photon. So what we're going to do is take that number from up there, the overall energy, 1.98 times 10 to the 5 joules, and we're going to multiply that, or we're technically dividing, but just so we can stick with the unit canceling, we will multiply that by 1.23 times 10 to the negative 18 joules for every atom. So, when you do this math, you will get, unit-wise, you'll get atoms. Sorry, that kind of cut off. And so unit cancel, joules is gone, atoms is all that's left. And when you do that math, oh crap, I didn't do it beforehand. Calculator. Or give me like half a second. 1.50, that's right. I wrote it on the paper. Okay, it's a 1.50 times 10 to the 23 atoms of carbon. That is what you get. Now, we'll see tomorrow how she does this. See if she does the same setup I did, but that is how I did it once I took a second to actually think about what was going on. So again, really quickly, we're only given a lambda and we're given an energy, the overall energy that's released. So with that, we don't have anything that would tell us, like basically break it down to the atom for us without doing some manipulation, and some of these questions you're going to have to do that. So we took the delta E equals HV, that's just the change in energy, which can also be written as E equals HV, the energy. And we found out for the V, which is nu, bad habit of calling it V, we used the speed of light equals lambda times nu, solve for nu. So we got nu equals the speed of light divided by lambda, and we plugged that in over here. And when we did that, we got this new equation, the delta E, or just the energy of photon, or the energy of the atoms, because again, 1-to-1 ratio. And that's going to be equal to Planck's constant times the speed of light divided by lambda. When you do that, that will give you, again, the energy per photon, which is the energy per atom, and you have the overall energy. So if you divide the two, you end up with the number of atoms present, which, again, 1.50 times 10 to the 23. So a little bit less than a mole there, because a mole is 6.022 times 10 to the 23. So pretty close, but not quite there. What is that, like a quarter of a mole-ish? Yeah, anyways, that's what I got for the answer. I hope this helped a little bit. I know it's kind of sloppy and super quick thrown together, but it wouldn't be polished if it was right in front of you either. So I, again, hope this helps, and I look forward to seeing you guys tomorrow if you watch us today, or whenever you watch us. Look forward to seeing you the day after that. Alright, take it easy.